Okay, good morning, guys. Okay, so I didn't sleep much last night. I might talk nonsense today. Just excuse me. You might lose track of what I'm saying. So for the project, you guys all know you will be presenting it on Friday, right? So I just want to remind you guys, I'm not sure whether everyone knows, I talked about it in class, you will have to propose 2 extra functions. Is that news for you? No? Okay, then I'll just assume everyone will do it, 2 extra functions. On top of those 11. Okay? So today, we'll continue the relational algebra from last time. So these are the couple of operators we learned from last time. So these are more like the basic ones. The first one is selection, so we use sigma to denote that. Anyone can tell me what the selection is? What is it for? Select rows based on the condition given to the selection, right? The second one is projection, so we use pi to denote that. What does projection do? So if selection can filter out rows, how about projection? The other direction. So projection, you can specify the fields you want to keep. So that filter out columns. Okay, so that's selection and projection. How about union? If we take the relation R with relation S, we're taking union of that, then the result will have what? Like the tuples that are in either R or S, right?
Either,
yeah. How about intersection? Yeah, if it's intersection, then the tuples in the result will have to be in both relation R and relation S. Correct? Okay, the next one is set difference. So if we take a set difference between R and S, we say R taking a set difference on S. What are the result tuples? I feel like everyone's sleeping. Come on, wake up. So if we take R, a set difference on S, the result tuple are the ones in R, but not in S. Remember? Okay, how about cross product? If we take cross product between R and S, it gives you a big table that combines all the possible combination of tuples between R and S. Okay, so just talk through what each of them do. So which are unary and which are binary?
Selection, projection, unary.
Yeah. So selection and projection are unary because they only apply on one relation. And the other, the rest, are binary, right? Because they will have one relation on the right-hand side, one relation on the left-hand side. So, which operator need the relations involved to be union compatible? If you remember what I mean. Union compatible means basically the schema has to be the same. So the input, the schema has to be the same. Then which operators will need that? Intersection and union. How about set difference? As well, right? So 3 of them, these 3 you need to have the input to relation having the same schema. Okay? So which operators will give you the input and the output same schema?
Selection.
Selection. And oh yeah, so which operators, when you give in the inputs, either it's one relation or multiple, the result will have the same schema.
Projection.
Projection is the one selecting columns. So that might change the schema, right? So selection, you already know, it will keep it if you don't apply projection on it. How about the rest?
Union, intersections.
Yeah, union, intersection, and set difference. They will all give you the same schema. Okay, last question. Which operator, the order you put the relation matters?
Set difference.
Yeah, set difference, right? Because set difference is when you take the set difference between R and S, if you put R minus S, the result is the tuples in R but not in S. If you swap it, then the result will be in S but not in R. Okay, so last time we did an example on this. On the slides, I made the same mistake as last time that got pointed out. So I didn't put the ID is supposed to be 101. Okay. So I put that in red. Don't forget to correct that. Last time we did that at the very end of the lecture. So we were basically trying to find the sailors' names who reserved boat with VID 101. But I didn't talk through how at each step the table will actually look like, so I want to spend a little time today to talk about that. So if we just basically look at this answer right here, we know like the first thing we do is the most inner part of the parenthesis, right? So the first thing we do when we did the union between instance S1 for sailor and instance S2 for sailor, that gives us all of the sailors, okay, in S1 and S2. That's what union does. And why did we take a cross product between this and the reserve table? Why would we want to take cross product?
We need the drawing so that we find the result.
Yeah, because now we have the sailor table, right? That we union them together. If you take a cross product, then they will be in something get associated with each other into a big table. Okay, so that's that for that part. And here we did selection. So we only keep the rows where the SIDs match, right? Because when it doesn't match, it's useless. So we only take the one that match. And then, according to that, this one. So we only take the one with boat ID 101. Okay, that's for selection. So that gives you the rows that you want. So why did we finally do that? Yeah, because we asked for the name, right? We find the sailor's name. So you only do projection to return the desired field. So I'll go through the table step by step. So this is what's going to happen first. Okay. So the first thing is we take the union between S1 and S2. So this gives you the tuples that are either in S1 or S2. Okay, so that's the result for the first step. The second step is the big cross product. So it will take, you can refer to the previous slide for the table. So it will take the product, cross product between this one and the R1 table. Right? So as you can see, how we will write it here is because for reservation we have 2 rows in total. So you kind of just double every single one tuple from here and then cycle through the R1. So that's what's going to happen for cross product. So I want to take a really quick note on cross product. If we say, this is kind of tiny, but I guess you can see on your slide. If we say A taking cross product with B gives us the result C, what's the cardinality of C? Remember which direction is cardinality? Number of rows. So what will the number of rows of C be? Yeah, the number of rows of A times the number of rows of B. So that's the 2 cardinality product. So that's for the cardinality. Then you can figure out what's the degree. you look at how many fields the result has.
The sum.
Just the sum, right? You just plus 2 together. So that's for degree. So just remember, when you take a cross product between the tables, the final result is actually the product of the cardinality times the sum of the degree, that big. So that's the second step. Now we got that. In the third step, we filter out the rows we don't want. I made a mistake here again, but you can refer to the previous one. So we only keep those. Oh yeah, I made it wrong. We only keep those we want. Here is different from the previous one. So we actually just want to keep the BID that's 101. So supposedly we shouldn't have this, right? But here, anyway, if you follow this, the selection, judging by the criteria, we only leave the rows that satisfy that. So we only leave these because the SIDs are the same, right? SIDs are the same. And finally, the final result, we only do the projection. We do the projection on only S name. That's what we got. So right here at step 3, as you can see, there is a problem occur because when information comes from the Saylor table and the reserve table, they both have SID, right? So here I actually just assume that we will call them S or R1, so you know where they're from. But when you really need to write them in relational algebra, this is where we face the naming conflict. So this is why we will need renaming, okay? So here I put the example again. I don't know why I did that. There was already example in the previous slide. But anyway, just make sure you can refer to and know what data we're talking about. So yeah, slide 6. Here's where we need renaming, okay? Mainly, we have 2 reasons for renaming. The first one is, as I said, is because we want to resolve the conflict. A lot of times after a certain step at the result, intermediate result, you will have the name from different relations that are the same. So by using renaming, we can know which field that with the same name is actually from, which relation it's from. Okay, so here's an example, the result of S1, taking cross product with R1, there are 2 fields with the same name, SID. So later I'll show you how we can do renaming. Another reason is actually we can break large expressions into smaller ones. So we can give names to the result of sub-expressions. For example, right here, this bigger relational algebra we did earlier, it's pretty convoluted, like you have so many parentheses in between. So you can actually break them down. Like when you write code, you will want to write this at the first line and then assign them to some variable. Okay, so renaming is actually the exact same thing. So you just break them down and have a clearer idea of what you're doing. So how are we going to do renaming? This is the syntax for renaming. For F, this actually is an overline, but somehow they kind of overlap together. But there's an overline, according to definition. So for renaming, we use the symbol rho, this one, okay, to denote renaming. And right here, the E is the relational algebra expression. So for every relational algebra expression, the result is still a relation, okay? So here in input, you can still use it just as a simple table. You don't need to use it as a relational expression. It's just when you have relational algebra expression, that's when you actually need renaming. Okay, so the later one is the input, and R is the name of the new relation for result E. So for example, earlier, RE will be S1, taking product, cross product with R1, then you can rename it with something else. And here is the trickier part. So F with an overline, we call it the renaming list. So it's just a renaming list. You can put the old name saying, so now the new name is this. Okay? And if they are all having the same name like SID from both S1 and R1, you can just put in S1, the SID, I want it to become what? Okay, so that's for renaming. So remember last time we said to refer to an attribute, you can either use position or the name. So sometimes you can also just use the position. For example, you can do S1.1, then we know it's the first attribute. Okay, so that's for renaming. So the field name in R is the same as the E, except for those renamed in F. So if you don't specify the newer name in the renaming list, then the result will just keep the same name. So let's see how we can do that. Here's an example. So we want to use the S1 taking cross product with R1. So as we know, if you look at the previous table, that has a lot of fields in the result, right? So this will be the schema for the result. We have not done any renaming yet, so we just keep the name for now. So as you can see, both have SID, right? So then this is where it actually creates the naming conflict. So we want to avoid this situation, to avoid confusion. So that's why we will need renaming. Okay? So as I said before, you put here, after the comma, you put the input of a relational algebra expression. So that's the one we want to do renaming. So we put it right here into the row operator. And what does the C mean? Yeah. So then this is the variable that you can say for S1 cross product R1. Okay, we want to call it C. So what's within the parenthesis? Yeah, so this 1 and 5 right here directly refers to, this is the position 1, and that's position 5. So we just directly call it. Okay, and we say we want it to become SID1, and the fifth field become SID2. So this is what you will get finally. So now you can see both field names changed, and also here we renamed the whole relation. Okay, so from here to C. That's for renaming. Any question on renaming? Pretty obvious, right? So just to prevent any confusion or ambiguity. All right. The next operator I want to talk about today is join. So there are a couple of different types of join, so I put joins. Join, we use this symbol to denote that. I actually don't know how to pronounce that, but just remember that one is for join. Do you guys know? Is there a name for that? No. Okay. Then just remember that, the butterfly-looking thing. So join is one of the most useful operations. Yeah, I was trying to do that symbol on PowerPoint. I couldn't find it. So I searched like the cool symbol list, like they have so many symbols. And I couldn't find them because I didn't even know how to do like Ctrl F. So I was just like, looking through the whole list and I found it. So join is one of the most useful operations and most commonly used ways to combine information from two or more relations. If you can recall, last time we were doing the example, we want to somehow associate between sailors and reservations. So that's why we took the cross product, right? Took the cross product first, and then we actually need to do a selection to find where the SID match. So this thing, as you can imagine, is actually done pretty commonly, pretty frequently. So if we always do cross product first, then selection, cross product, selection, it's kind of annoying. So you can just come up with join that do two steps together. So, according to what I just said, what is join equivalent to? What then what? Cross product? And then selection. Sometimes we would use prediction. Okay, so this is what join is equal to. Okay, so there are a couple of reasons that you want to use the join operator. First one is, as I just said, joins are used so much more. They cross product so often, so we want to just have this useful operator. The second reason is actually, as we saw before earlier, you filled out the cardinality and degree. The result of cross product tend to become very big. Okay, so in the intermediate step, they will actually get stored, that big table, it will get stored. But if you do join, they can be do together. So after you do the selection, the bigger table will not be stored. So it's just easier and saves space. So there are 3 types of join. The first one we call the condition join. So we use the symbol, join symbol, and you put a C, which is the condition, in the subscript, then that's how you do the condition join. Okay, so you would join relation R and relation S based on condition C. So this is actually equal to, as I just said, you take the cross product of R and S first, and then you do a selection on condition C. Okay, so those are equivalent. So the condition is the same as the one we learned in selection. So it can either refer to relation R or relation S. Here's an example that we want to try. So this is the condition join on S1 and R1, where the S1's SID is smaller than R1's SID. Yeah, so that's that. Can you imagine why it happened? So actually, in the background, they take the cross product of S1 and R1 first. That's why we have so many fields, right? The degree is so high. So the degree is S1's degree plus R1 degree. Then you simply take the rows that satisfy this. So if we only use the operators we learned from last time, then you will need to do both cross product and selection, but this time you do it in one condition join. So as you can see, the result schema is same as that of doing one. Taking a join, the result schema is the same as taking one. It's the same as taking cross product. Because as we said earlier, the first step is to take the cross product, and that gives you this number of degree. And doing selection actually doesn't change the schema, right? So that's why we say the schema is the same as that of cross product. So that's the first type of join. The second one, yeah, that's a fail. The second one, it's used so often that they just call it equijoin and there's no space in between. So it's a special case of condition join where the condition contains only equalities. So in the previous one, we said where we want to keep the rows where the SID from S1 is smaller than SID from R1. But here, equijoin is just a special case. So if we only say, okay, we want to compare SID, and as long as it's the same. So you can just write that, but this is actually equal to this. Okay. But the condition will be when the name is the same, so that you can put that. Okay. If not both S1 and R1 name it as SID, then you can't just put equijoin on SID. Oh, so here I made a mistake. So the result schema will be similar to the one of cross product, but it only keeps one copy of the field for which equality is specified. So actually, cross that out. This won't be here, okay? So if you do equijoin, they will just only keep one field that you specify to do the equality comparison. So it's similar to the cross product schema, one field different. So that's for equijoin. Okay, and the very last one, it's not that commonly used. It's called a natural join, so you don't put any condition. So it's a further special case of the join that it compares all the equalities between the fields that has the same name. Okay, but that doesn't happen that often because normally we compare between the primary key and the primary key both table, that might be the only field they have the same name. So this idea is just saying, okay, we would look for all of the fields that have the same name between the two relations and make sure they are equal. Okay, so this is natural join. The more commonly used ones will be condition join and equal join. I feel like I might finish earlier today. That might be great. Okay. Okay, the last one. Actually, this is the last concept I want to talk about today, but it might take forever. I'm not sure. It's called division. Okay, so division, before we get into what division actually is, in the following few lectures, our example got a bit bigger. And this time we have both information. Okay, so forget about the previous one, now we work on this. So if you look at this table, what would you do if you want to find the names of the sellers that have reserved all votes? Do you think, based on the operators we learned earlier, you will be able to do that? Maybe through a lot of steps. Anyone has any thoughts of how you would do that? No? Okay.
Join three table
With
like the ID of the B1 equal to the ID of the R2, and the SID of R2 equal to the SID of the S3,
mhm.
and then get the vote from the S3.
But how do you make sure the seller reserves all of the votes?
Like one cell.
We want the sellers that, so for the return sellers, for each of them, you want to make sure they reserve all of the votes. Okay, so this is where we need division. So let's start from easier concepts. So let's say we have relation A and relation B. And assume A only had two fields, X and Y, and B have only field Y. And our goal is to find X that associated with all of the Y's. Okay, so you can just think of it as this. We have an A. Can you guys see that from there? No? Okay, I'll draw a copy of it. Okay, give me 1 second. So I want to see, this is relation A. I field X and Y. Okay. Relation E. Field Y. So we want to see when we compare, the B gives you an idea of how many Y's are there. That means all, okay? And you want to make sure, for example, we only have 1 and 2. And if you have an A that has an X that's, I call it A. Yeah, A, okay. And if you have like 1 and 2, then A is this. Today you only have a, let's call it C. Only associate with 1, then C doesn't sense. Can you guys see that from there? So that's what we want to do. So if you want to write it in the set definition, like we always do with the curly braces, this is what you would do. It looks super crazy for now, but it's actually pretty simple when you break it down. Okay, so according to the definition here, we want to get all of the X that satisfy the condition where there exists a tuple called xy that is in A, so that for each y, it's in B. Or for all y is in B. Make sense? Okay, so that's the definition for A taking a division on B. So we are finding the x in y that associates with all of the possible y. No, x in A that associates with all of the possible y that is hinted at B. Okay? So there are two ways to interpret that. The first way, I think, is just similar to the one I just said. So it's A taking a division on B. The result contains all the x tuples, such that for every y tuple in B, there is an xy tuple in A. Somehow make it more complicated. But second one, if the set of y values associated with an x value in A contains all y values in B, the x values is in A taking division on B. Okay, so you might think, why would we want to use this idea and call it division? So there's one way of thinking about it. So if you do an analogy on the integer division, okay? Let's say we want to, let's imagine today A and B, and not imagine them as integers. If we take the division A divided by B, let's just think of it when you're coding, so the result is still integer. Okay? So the result should be smaller than the actual answer of A divided by B, right? So when we do that, A divided by B, when A and B are both integers, if the result is Q integer. We want the Q to be the largest integer such that when you times Q and B, it's still smaller or equal to A. Okay? This is what we normally do for integer division. So if you think of it as our relation instances, today we changed the concept from integer to relation instances on A and B. Then A taking a division on B should return you the largest relation instance Q such that this will satisfy. So it means such that when we take a cross product between Q and B, it should still be a subset of A. Okay, so how will we think about it? Let's go through an example so then you can have a clear idea. I was supposed to take out the answer out, but I forgot. I just print them all out so you guys have it. So let's try. We have these A, we have a big A and 3 smaller B's. And I want you to think about why you would get those results when you take division. Okay? So the first one, we take division. A divided by B1. What would you do? So here we have, if you only look at it, so this left column in A, you can imagine it as the X right there. Okay? And here is the Y. Okay? S number is X, P number is Y. Okay? Stop me if you feel like you're still confused. So right here at the X, you can see for A we have 4 different values for S, right? S1 until here, S2 until here, S3 only here, and here's S4. Okay, so we have 4 possible values for the X in A. We want to find the ones that satisfy the requirement where they are associated with all of the Y's in B. So if we only do the first one, then because it only has 1 value, only P2. So whoever have associated with P2 in the A table will be in the result. Okay? So let's check the first one. Does S1 associate with P2? Yeah, here. Okay? And how about S2? S2 as well. Associate with P2. S3 associate with P2. S4 associate with P2. So that is why in the result we have them all. 1, 2, 3, 4. Okay? Let's try the second one. So the second one we want to find this time the S's that associated with both P2 and P4. So if you look at S1, only until here, right? Does S1 associate with both P2 and P4? Yeah, 2, P4, right? How about S2? Not anymore, right? S2 here only associate with P1 and P2. So S2 disqualify. How about S3? Disqualify. S4? Yeah. So then that's why we have the result. S1 and S4. Okay, want to go through the last one, or you're all good? Okay, you can figure out the last one. Okay. So let's see. So this is the concept of division. And actually, we can express division by using the basic operators we learned before. And then that's where things get a bit crazier. So division is not an essential operator. And it can be expressed using the basic operators. Another example that we learned is the join, right? Join, we can also do it with other basic operators. So how would you do it to write it with the simpler operators we learned? The idea here, remember earlier I said disqualify when we were going through. So we will use the concept disqualify. We will take out those that don't qualify. Okay? So I want you to, I'll use the blackboard and do it together. Alright, so the first thing we want to do, since we are actually doing things between A and B, so whenever we want to do something, some kind of association between two relations, what do we do? What do we do to make them into one table? Cross product. First thing first, you take the cross product. Okay, then think about the previous example where we have A with 2 columns, B with 1 column. Okay, so if you do the cross product, it will actually give you 3 columns, right? And because they already have one field in common, do you want to still keep the other one? To keep this one? Or we only need one? Only need the one that B doesn't have. Correct? So what can we do to make it smaller? To keep the one that B, only keep the one B doesn't have from A. Projection. Okay, we do projection on A. So what you can think of it is, we do a projection on A, and that gives you only this column. Take a cross product with this one. Okay? So then the result should give you something with X and Y. Again, schema is still X and Y, but this time X is from A, but Y is from B. So then you can make sure this Y actually contains all of the Y's, because it's not guaranteed the Y's here involves all of the Y's in B. You following me? Okay. So that's the first step. Okay. So what do you think this will give you? Let's say here we have and maybe here we only have 1, 2, 3. Okay, so if we do this after the cross product, here will actually completely transform into, so that would be all of the possible x in A, taking cross product with all of the possible y's in B. So then that will give you one, 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 two, 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 and then three, three, three. And then here it will be 1, 2, 3, 1, 2, 3. Make sense? So this will be all of the possible combinations, but as you can see, if we compare this, okay, let's put this C. If we compare this with A is actually smaller than that. Okay? It's possible to be equal, but like smaller or equal to this. So what do you think will happen? So this is the result of C, right? What do you think will happen if we directly take a set difference between these? Then what does this mean? It's saying the whole thing will result in tuples that are in here, but not in here. Okay? So the result of the whole thing for now actually means none of them are in A. Right? So we call them the old disqualified ones. All disqualified tuples. So if we recall, our goal is to get the ones that A has. So what do you think we will eventually do? Now we get the disqualified ones. We want the ones that are in A. So recall the goal for division. We are finding the x that somehow associate with all the y's in A. Okay? So here, what you will finally do, what would you finally do? Take it out from A.
A doesn't have any of the tuples in the second. These are all the tuples that are not in A. So, so we can do that, but it just give us back A.
Let me see. In here, but not in here.
If you projection.
And then so all those are disqualified. My brain got stuck, but I think we can do that. Wait, here, I'm gonna see. Wait, write that down first.
We can do that.
We can?
Yeah,
We can do that, but it'll just give us back A.
No.
Because what we're doing is we're
No,
getting.
it's not.
No.
No, it's not A.
Because this part makes a big difference.
Yeah.
Yeah. Have you guys all write that down? I put the steps in example. We can take a look. Okay. So we can see where that.
If we take the projection X like in the slide, then we can do it. Without the projection, you're just finding out.
Oh yeah. Projection of. Yeah. Oh, you said here, right? I missed one step.
And then you subtract it out of it, so you get all
Yeah,
this.
but because you have, you can see from the table, you subtract A from there. What's originally A is 1, 1, 2, 3. And when you have the whole, the following in
Whole
C,
minus A
yeah,
with
and-
B is 2, 3. With 2, 1.
no, if you minus A, you have 2, 1, 2, 3, and 3, 1, 3.
Which are not in A.
Yeah, and then you subtract them, you get 1, 2, and 3, which satisfies. And if you choose protection from A, you get the final result of what you want.
Let's directly
That's
do
step
that.
one.
3, 3, 3, 1, 2, 3. Okay, let's extend that from here. All right. So that's here, correct? That's cross product. Take it out. Take the ones that are in here but not in A. So then we will keep. We will keep the one in here but not in A. So this one will be out. This one will be out. This one will be out. This one will be out.
Now without taking the projection, if we subtract, then we just get that.
And then now we take the projection.
After projection it will work, but without the projection it will work.
Yeah. So without projection, that was wrong. So because with the projection, then now we get only 2 and 3, right? So we call them the disqualified ones. Yeah, you're right. And then we take out from all of the possible x minus this. Yeah, thank you. Yeah, I missed that part. So that makes a big difference. Let's see it in action. So here's that. All right, so here's a bigger example. As you can see, here's the part when we take the cross product, right? And here it's essential, we need to take the projection. So we give a non-duplicate set of the possible x's. And finally, we use all of the x's in the original A, taking out the disqualified ones. Okay. Yeah, sorry for the confusion. So that's that. Okay with that? Okay, final thing. I think I only have two slides left. Perfect. So here is just the operations that we learned so far. Just so you don't forget. Okay, we learned selection, we learned projection, cross product, set difference, union, and intersection from last time. And today we got join. Don't forget, join has 3 types of joins. And we learned division. And also we learned rename. Okay, before you go, a couple of things, don't forget. So you will want to remember the project presentation on Friday. And homework is due next Friday. I'll try to give you the graded homework for homework 1 by this Friday. Okay? And don't forget, midterm is actually coming really soon. Next Tuesday. Almost 2 weeks from now. And it's an evening, so don't forget. What? Yeah, there will be a review session the day before.